We better have some answers now. Again, every time I see that logo, I feel like we should answer something.
Have you seen it in full screen mode yet?
Yeah.
Well, it's amazing. It's really impressive.
Yeah.
Really puts the pressure on us to have actual answers to something.
Answers in atheism. Yep.
Yeah.
So,
Too bad our hearts are empty and our lives are useless.
Yeah, well, our lives hopefully will fill up again after the next year. Maybe. I don't know.
Maybe so.
We went to the grocery store, and that was exciting with my new superpower vaccine powers. I have superpowers now.
Yeah, you can kind of walk with a little confidence, maybe a little cocky.
Yeah, a little bit of a strut in my steps, and I
That's
don't.
right.
I don't have to belly crawl across the floor, or
You don't have to run screaming from people approaching you.
Yeah, check my 6 o'clock for approaching seniors. I don't have to do that. Yeah. They sneak up on you, those seniors. There's fewer seniors now that I'm 70.
I know. You keep looking around for them, and they look normal.
And they're slower. They're a lot slower than they used to be. They used to have a little spring in their step, and not anymore. So, anyway, we have a new paper here by Daniel J. Nicholson, which came out of a book. We should probably post a link for the book. I believe I posted a link for the paper. The paper itself is in Phil Papers, and I posted a link in the description, but I don't think we're going to read the entire paper because it's 24 pages, but we're going to at least do the introduction. This is an amazingly popular stream. People are just flocking to watch us read papers, right?
I know. It's the latest thing in geekdom.
There's 5 now, 5 people. So,
but we could skip the whole middle part because it's just assertions anyway.
Is it just assertions? Yeah, we can just go to the conclusion.
We'll just use the Otangelo method of reading papers, and that's to not read the whole paper and just stick with the abstract.
Well, yeah, this on being the right size. How did he get to be the right size? I mean, how could that happen? Naturally. Couldn't happen naturally.
Yeah, 1926.
Okay. So you want to go ahead and get us started?
I'll be happy to. In 1926, Haldane published an essay titled On Being the Right Size, in which he argued that the structure, function, and behavior of an organism are strongly conditioned by the physical forces that exert the greatest impact at the scale at which it exists. This chapter put Haldane's insight to work in the context of contemporary cell and molecular biology. Owing to their minuscule size, cells and molecules are subject to very different forces than macroscopic organisms. In a sense, macroscopic and microscopic entities inhabit different worlds. The former is ruled by gravity and inertia, whereas the latter is governed by Brownian motion. That's a good insight right there. It really is. One implication is that we should be extremely skeptical of models and analogies that seek to explain properties of microscopic entities by appealing to properties of macroscopic ones. Unfortunately, this is precisely what the appeal to engineering metaphors in molecular biology attempts to do. Molecular biologists routinely resort to such metaphors because they are familiar and intuitively intelligible. But if our machines were the size of molecules, it would be impossible for them to function the way they do. It follows that we should avoid distorting biological reality by construing it in engineering terms. In this chapter, I examine 4 key metaphors in molecular biology: genetic program, cellular circuitry, molecular machine, and molecular motor. And I argue that their deficiencies derive from their neglect of scale. I also try to explain why many biologists today appear to have forgotten the importance of scale that Haldane drew attention to in his essay. I suggest that the reason has to do with the influence of Schrodinger's argument in What is Life regarding the stability of the gene.
Okay. So, how are we going to handle the rest of this?
Okay, I want to, real quick, I want to type in the title of the book that this is a
member of.
Yeah.
Yeah, Aristotle compared the bones and the tendons of the forearm to the arms of a catapult, drawn back by tightening ropes. Descartes was so impressed by the lifelike movements of hydraulic automata that he concluded that the movements of the body were machine-like. And Liebig's view of digestion as combustion relied on his understanding of the body as a heat engine and the food as fuel. So Schrodinger made some other errors, apparently, because earlier today we were doing that thing on entropy, and Schrodinger apparently misappropriated entropy in life, and the author that I was reading said that makes no sense at all. I'm trying to apply entropy to life. Anyway, so I suppose we're going to be stuck with reading the beginning of this today. So I think that covers that paragraph.
Yeah.
But do you want to continue and just try to read? Because let's see. Well, let's take a look at the outline of the paper. So we've got that, and then we start redeploying the argument of Haldane's on being the right size. So redeploy, okay. And then and we've got, let's see, what are the sections of this thing?
Well, there's an explanation that takes into the something qubit law, and then why we're not 10 times bigger than we are.
Right. Then we get on to metaphor number 1. So maybe we can make it that far today, but I will go back up and we will see what we can do.
Okay. Well, by the way, I put the link to the book in the public chat.
Good. Okay. And I will try to link
and this chapter, you've already got the link to the paper, right?
Yep, I got that in the description.
Yeah.
This particular chapter, and I will put this link to the book in the description and save it. Cool. Okay. Let's see. Where are we here? Let's see. And computer science has furnished biologists with an even richer array of technological devices to employ as models in their explanations of the phenomena they investigate. However, despite their undeniable heuristic value in certain experimental contexts, machine metaphors can be seriously misleading when they are used to ground the conceptualization of biological phenomena. I just want to interject here that one of the things that I learned some decades ago was that when it comes to water in the cell, it's not that porous stuff that we're used to.
Yeah.
The swishy porous stuff. It's more like a little syrupy stuff. I mean, it's pretty sticky at that level of magnification, and things are very, very different in cell. And recently, I heard that there's a protein, like within, like if you imagine the diameter of a protein and say that's a basketball, well, one diameter or less away from that will be another protein. So the cell is just chock full of proteins and other molecules, and amongst them you have all these ions and water molecules, kind of like sticking to things, and sort of gooping around. Yet, at the temperature that we live at, it's still going very, very fast. And if you were down there, things would be zipping by your head pretty fast. Well, of course, you would be instantly killed.
That's right.
Yeah, as if getting hit by a tennis ball going 9,000 miles an hour would be fatal. Anyway, okay. What did I read? The reason is that some superficial similarities notwithstanding, living systems are fundamentally different from machines. Ontologically speaking, the machine conception of the organism, hang on a second, we had a problem, Houston. Machine conception of the organism, as I have referred to in the past, is fraught with problems. In previous work, and I believe, was that the last one we read, 2018?
Well, we did a 2019. He's noting the 2013, 2014, 2018 papers. one thing I want to say is just as a lesson, kids. The reason why you want to read the middle part of papers, unlike what some of our creationist friends will actually literally say, is because they're not just bare assertions. They are assertions with backup. Notice these parentheses after, pretty regularly after a sentence or a paragraph. That is an indication you can go find the papers and the publications that are being referred to and look them up so you can make sure that what is being said is backed up by those papers, and that those papers actually support the premise that Nicholson is trying to bolster. That makes it educational, that makes it informative, and that makes it makes you not 100%, but a whole lot more likely that you're getting to the reality of things. Or maybe not. Maybe you can spot a flaw. Maybe the arguments don't support the thesis, but you won't really know until you get deep into the background. That's enough of my soapbox.
Okay. I just realized that you put your search term and you misspelled philosophical.
Oh, where?
That link basically is your search term. It's not the actual link to the book.
Oh, I'm sorry.
I replaced it. I replaced it. So
okay, I appreciate that.
But I love the word
philosophical. Okay, I'm going to remove my link in the chat, and you just replaced it. So cool.
Yeah. So philosophical things are not us.
Philosophical.
Philosophical.
That's something for people who are drinking at bars. That's their philosophical definition.
Philosophical opinion.
Mm-hmm.
I have advanced two major arguments against theoretical understanding of organisms as machines, which still pervades many areas of contemporary biology. The first, which can be referred to as the argument from teleology, states that organisms are intrinsically purposive in the sense that their activities and internal operations are directed toward the maintenance of their own organization, whereas machines are extrinsically purposive, given that their workings are geared toward fulfilling the functional ends of external agents. That is a nice one, okay? I like that. There's a very, very big difference. Life sustains itself and reproduces itself. It doesn't produce products or like a factory, and factories do not sustain themselves. External agents do that. You hire somebody to come in and fix the roof on the factory, right? The factory doesn't. The purpose of the factory is not to fix itself and keep itself factoring.
Right.
The factories factor? I don't know. There's a philosophical question for us. The second, which can be referred to as an argument for thermodynamics, states that organisms exhibit dynamic stability due to their need to constantly exchange energy and matter with their surroundings to keep themselves in negotropic, steady states far from equilibrium, whereas machines exhibit static stability, given that they do not require to constantly expend free energy to ensure their continued preservation as they slide back and forth from equilibrium to near equilibrium conditions. There again, factories do not sustain themselves. I have shown that the former argument has especially salient consequences for development and evolution, whereas the latter argument has particularly important implications for morphology, physiology, and bioenergetics. And I just want to say something about the extended synthesis of evolution. Mm-hmm. It shies away from the idea that the environment shapes the organism. Granted, the environment and does shape the organism, does shape natural selection, but there's also a shaping of the organism from within and from its own history. Mm-hmm. So what the organism can morph into is based on what it used to be. Like we are always going to be apes. Okay, and the environment has nothing to do with why we're always going to be apes. We're always going to be apes because we always were. So there's this internal, they call it evo-devo in the extended synthesis, this internal constraint over what a cell or what an organism can become in evolution. And that's kind of similar to this idea that there's no teleology, there's no outer purpose for it.
Right.
And I think ideas like survival of the fittest, that phrase, are ideas that we should rip from our mouths, toss on the ground, and stomp them, because that's not what happens. Even though it kind of does in a way. Sometimes, I mean, that's one aspect of the system, but thinking in those terms will not get you to understanding evolution as it stands today. So anyway. Oh my God. Fucking Danny's here too. Oh, don't get me started, Danny. Can I shut off the chat? I don't know. Okay, your turn in this chapter.
In this chapter, I draw inspiration from a classic essay by Haldane titled On Being the Right Size, first published in 1926 to propose a third argument against the ontological identification of organisms as machines that is especially relevant for current research in cell and molecular biology. I shall refer to it as the argument from scale. Roughly, this states that owing to their minuscule size, cells and their macromolecular components, even more so, are subject to very different physical conditions compared with much larger objects like machines. Machine metaphors and analogies draw on our intuitive familiarity with the macroscopic world of our everyday experience, but such intuitions fail us when we attempt to grasp the structure, function, and behavior of microscopic entities, as these exist in drastically different environments from our own and our machines. In the ensuing sections, I will illustrate this argument by critically examining 4 conceptual models of molecular biology that were originally imported from electronic and mechanical engineering, namely genetic program, cellular circuitry, molecular machine, and molecular motor, and by showing that their explanatory deficiencies ultimately derive from their neglect of the impact of scale. But first, it shall be useful to remind ourselves of the claims that Haldane put forward in his essay to better understand how they can be fruitfully redeployed in a contemporary context. At the end of the chapter, I will try to explain why so many
and you have to have an operator error. Okay.
Molecular biologists today appear to have forgotten the importance of scale that Haldane famously drew attention to in his essay.
Okay, I'll take over.
All righty.
So I guess we are reading. Promise next time we'll try to be more concise and maybe do some highlighting and summarizing. So, but
sure.
But I don't know. It's okay. Okay, although Haldane is primarily remembered for his foundational contributions to theoretical population genetics, he was also a prolific essayist and an avid popular writer who wrote numerous articles on a variety of topics. On Being the Right Size is one of them. Its message is simple, but it has profound consequences. For every type of animal, Haldane writes, there is a most convenient size, and a large change in size inevitably carries with it a change of form. Now that is really important to consider. I'm reminded of Standing for Truth's, what is that big red dog? Clifford-sized dog. And flea-sized dog. He asked, could a dog evolve into the size of a flea or the size of an elephant? That was like his first question when he first came on. And the size of the elephant one, the answer to that is, yeah, it could, given enough time, but it would have to change morphologically considerably. Its paws would have to go away. They'd have to become more like big flat pads and, many other changes. But size of a flea, no, that wouldn't be possible for a mammal. So
sorry, kids. Sorry, people who watched the movie Journey to the, what was that called? Incredible Journey, where they shrank everybody and shrunk shrunk Raquel Welch and put her in the middle of the blood system and
all
that stuff. And there was another one with not Melanie Griffith, but the other perky blonde of the 80s and 90s. I can't remember. Meg Ryan. It had Meg Ryan and Dennis Quaid in it.
Oh.
I can't remember though.
Yeah, I remember. I kind of vaguely remember it.
Yeah.
Yep.
Not gonna happen. Not gonna happen, folks. And the Honey, I Shrunk the Kids couldn't happen.
Nope. Fortunately. Well, I don't know. Sometimes, maybe not. I won't say it. Size directly constrains. I love kids. Size directly constrains the shape and structure that an animal can assume, as well as its behavior. An animal's way of life is conditioned by the physical forces that exert the greatest effect at the scale at which it exists. For example, gravity poses no danger to a small animal, but is a very serious threat to a large one. As Haldane memorably puts it, you can drop a mouse down a 1,000-yard mine shaft, and arriving at the bottom, it gets a slight shock and walks away, provided that the ground is fairly soft. A rat is killed, a man is broken, a horse splashes. An insect is not afraid of gravity, as it has a negligible effect on its way of life. It can fall without danger and crawl up a wall or cling to a ceiling with remarkably little trouble. Conversely, surface tension is of little significance to a large animal, but is of critical importance to a small one. A man coming out of a bath, Haldane observes, carries with him a film of water that's about 0.5 millimeter thick and weighs about 0.5 kilogram. Holy shit, I didn't... Really? A wet mouse. Yeah, actually, when I was really doing a weight loss program, you can lose like a pound or gain a pound. Well, you gain weight when you lay in a tub of water for a long time, and then you lose it like within a half an hour or so. That's interesting.
That is.
Anyway, conversely, surface tension. Okay, a wet mouse, however, has to carry its own weight in water, and a wet fly has to lift many times its own weight. In fact, once a fly gets wet and falls in the grip of surface tension of water, it is likely to remain there until it drowns. An insect going for a drink is as great a danger as a man leaning over a precipice in search of food, which is a reason why most insects keep well away from their drink by means of a long proboscis. That's interesting.
Now, I wish we had Brainbug here to confirm or deny that particular statement. He doesn't. Does he really support that? But anyway.
Yeah. Okay, I think I'm going to turn it over to you for a minute, Scott.
All right. Many of Haldane's examples are based on the square cube law, which states that the volume of a shape increases much faster than its surface area. Specifically, volume increases as the cube of length, while surface increases only as the square. A large organism has a far lower surface to volume ratio than a smaller organism of comparable shape. This explains why large animals have less trouble keeping warm than smaller animals, which cannot help dissipating more heat because of their higher surface to volume ratio. A mouse must eat about 1/4 of its own weight in food every day just to keep warm. And although 5,000 mice weigh as much as a man, their combined energetic consumption through food and oxygen is about 17 times a man. But small animals exploit their high surface to volume ratio in other ways. Insects have no need for complex circulatory systems. The oxygen their cells require can be directly absorbed by diffusion of air through invaginations in their external surface. In order to become larger, animals have had to evolve oxygen carrying bloodstreams as well as pulmonary alveoli to increase the surface area available for the exchange of gases. And a gastrointestinal tract to increase the surface area available for the absorption of food. Haldane realized that the higher animals are not larger than the lower because they are more complicated. They are more complicated because they are larger. And the same can be said for plants. In general, comparative anatomy is largely the story of the struggle to increase surface in proportion to volume. Such geometric relations determine the morphology and physiology of organisms, and impose unbreachable limits on their possible dimensions. Given their existing morphology and physiology, it is simply not possible for insects to grow to be much larger than they already are. For the same reason, the giant creatures found in fantastical stories from Gulliver's Travels to Godzilla are impossible. Haldane calculated that a giant, 10 times as high as a man, and also 10 times as wide and 10 times as thick, would weigh 1,000 times more than a man. But because the cross sections of its bones would only be 100 times those of man, every square centimeter of giant bone would need to support 10 times the whatever that is, because it's covered by that little.
So you're reading from the screen?
Yeah, why wouldn't I read from the screen?
10. Oh, I thought you were reading. I thought you were reading from the document. Sorry.
But because the cross section, I'm sorry, go ahead.
Oh, weight. Your next word is weight, supported by every square centimeter of human bone, right?
Okay. Wait. I don't know. Okay, there we go. The consequence of this is that the giant would break its thighs every time it tried to take a step.
Yeah. So I just wanted to comment on one of our resident commentators said something about essentialism when I was talking about the extended synthesis in Evo Devo. And that's because he is very ignorant. I believe that things have a set of characteristics which make them what they are, and that the task of science and philosophy is their discovery and expression. The doctrine that essence is prior to existence. No, that is not what it implies, Danny. Evo Devo is entirely different. Evo Devo is about constraints and mostly morphogenetic constraints, things that relate to embryogenesis. So it's a misunderstanding. The constraints are also external. So there's a combination of top-down and bottom-up constraints that have to be viewed. And in the past, it was considered just a function of the environment. So one might ask how something developed and just take into account some just so story about what happened in the environment. And you would be missing the point, because that isn't all that happened. Mutations create stochastically some features that didn't necessarily have to be created. And those features were constrained by what is morphologically possible in embryogenesis and the development of the cell. Okay. And then by the time it actually gets to be an organism in the environment, that's when the other part of natural selection takes over, and we figure out whether a rock's going to drop on it or whether it's going to get too cold for it to survive or whatever. So the extended synthesis is about taking into account more levels going from top down and bottom up in a cross hierarchical network of it's about dynamical systems, basically, and that's what it's about. So no one said that the organism has some essence that makes it into what it is in the next generation. No one said that. Did you follow that, Scott?
Yes, I did.
So, that's one of the important differences that we've the extended synthesis actually started, I think, as early as probably the 20s or 30s. There were already people thinking about this, and definitely by the 70s and 80s, it was taking hold, and it got its name, I think, in the 90s, something like that, and it's become a thing now. But anyways, it's sort of and there's a little bit of a fight between the traditional evolutionary crowd. They don't understand why we need. They would insist that they had always considered those things, right? We don't need a stinky new name, right, for evolution. And then there's the other group that's saying, we're the new boys on the block. We're gonna rename it. So that's what that's about. We are going to do some reading on the extended synthesis, so because it kind of comes out.
Well, these next couple paragraphs in front of us are just basically a way of saying Galileo understood this too, and even back, when he was around.
Okay.
And then he drew a picture, and that's kind of what Galileo said. bones would have to look like if you're going to increase the size of humans to.
Oh, so yeah, so he got it. He got it. Yeah, so Clifford dog would have to have big fat bones.
Yeah, they would have to be a lot thicker in proportion to
a fatter.
A normal size dog.
Yeah. Okay, the difference in size between a man and a paramecium is several orders of magnitude greater than one between a man and a giant, or between a mouse and an elephant. Now, that's an interesting little insight. These size differences are deceptive, sort of. As a result, the morphological and physiological differences between them are also far more dramatic. I've already indicated that the structure, function, and behavior of every organism are adjusted to the scale at which it lives. The scale defines the physical environment in which each organism finds itself and determines the forces that have the greatest impact on its way of life. Cells and molecules are so minuscule that they exist in an environment that is completely different to our own. Now, that is what I was talking about with sticky water. Yeah. You know, big, chunky, sticky water. Like
warm, sticky Jell-O or something. Although when you warm Jell-O up, it turns into sticky water. But,
it does.
But it's not thick, thick like say Jell-O.
So, you know that stuff you put on pancakes? What do you call it?
Syrup?
Yeah, we call it syrup.
Or syrup.
We call it syrup in northern Minnesota. We get into a lot of trouble with people.
Take away the syllables, huh? It's a one-syllable word.
Yeah, and then we also say go show. What are you going to do tonight? Go show. Go show
go
what?
Show.
Yeah. I don't know. Anyway.
Yeah, see a movie.
But I get a lot of shit from down south. Even my own children who grew up in southern Minnesota don't talk like us northern Minnesotans.
That's right.
Anyway. And none of us fucking talk like they do on Fargo, except the people that are actually from Fargo, North Dakota. Some of them actually do talk that way. So
North Dakota is a different state.
It is. And that's what really blows me away because Fargo's not in Minnesota. But the movie was named Fargo.
Yeah.
Anyway, okay, it's not an exaggeration to say that macroscopic and microscopic entities inhabit different worlds. Whereas the macroscopic, I got to let somebody in here. You want to let him in?
Sure.
Against better judgment. It's not whereas the macroscopic world is ruled by gravity and inertia, the microscopic world is governed by Brownian motion, which results from the thermal agitation of molecules above absolute zero. This has serious implications for explanations we formulate of cellular and molecular phenomena. Most importantly, our imagination and intuition, based as they are on our own experience of the macroscopic world, fail us when estimating the adaptive problems that cells and molecules have to overcome as they inhabit a world that is utterly alien to us. Mutable, you want to take over and read a little bit? But let's see what we got to read here.
Let's see what paragraph are we on? I just had a pretty involved conversation with a relative.
We're on the main lesson. Was it about whether you should get vaccinated or not?
Oh, fucking shit.
all my conversations with relatives lately have been about that.
Oh, how fun.
Yeah, it is fun. Enjoying it.
Let's see. The main lesson I wish to draw from this is that we should be extremely skeptical of analogies that seek to explain properties of microscopic entities by appealing to properties of macroscopic ones. Unfortunately, this is precisely what metaphorical appeals to machines in the modeling and explanation of molecular and cellular phenomenon attempt to do. We routinely resort to machines to shed light on microscopic structures and process because machines are familiar and intuitively intelligible macroscopic objects of our everyday experience. To conceptualize something as a machine is already to assume that we have a basic epistemic handle on how it works. The problem is that if our machines were the size of molecules, they would not be able to function the way they do, as their physical environment would make it impossible for them to do so. It follows, therefore, that we should try to avoid distorting the reality of cells and molecules by construing it using concepts and models borrowed from the domains of electronic and molecular engineering. Indeed, the reason why engineering metaphors in molecular biology mislead more than they eliminate, as the following four cases will illustrate, is that they are approximately calibrated to the scale of the target domain they are called upon to explicate.
Okay, so now we're into the section one. So did you hear any of the stuff I said about extended synthesis?
No, and unfortunately, I'll explain off air, but I was having quite an involved conversation
with
a relative.
Yeah. One of the parts of the extended synthesis, which we're going to get into a little bit, is the gene-centric view of biology, which is somewhat tamped down in the extended synthesis. So they shy away from the gene-centric view. So that's another part of it. That's just one more part of it.
Okay. All right. Okay. I'll do the next paragraph if you want.
Yeah, I would like that.
Let's see. The first engineering metaphor I shall discuss is the perennially popular notion that every cell contains a genetic program that directs and controls its functions by executing a predetermined set of operations according to instructions encoded in its genes. This idea was proposed seemingly independently by Jacob and Monod, 1961, and Mayer, 1961. And it quickly garnered widespread acceptance among molecular biologists. Jacob admitted that the genetic program is a model borrowed from electronic computers. It equates the genetic material of the egg with the magnetic tape of a computer, adding that everything urges one to compare the logic of heredity to that of a computer. Rarely has a model proved to be more faithful. Mayer, for his part, remarked that all manifestations of development and life are controlled by genetic programs. Hold on. Nothing comparable to it exists in the inanimate world except for man-made computers. More than half a century after it was first proposed, the metaphor continues to pervade the specialist as well as the popular scientific literature. Despite its enduring popularity, the problems with the genetic program have long been pointed out by biologists and philosophers, Webster and Goodwin, a bunch of them are listed here. It has been repeatedly argued, for example, that the metaphor is conceptually incoherent, as the genetic program requires its own output to be executed. The protein hardware that runs the genetic software is not independent of it, but is itself produced by that very software. What has received far less attention, however, is the fact that the difficulties involved in theoretically transferring the idea of the program governing the operation of a computer to the way genes are involved in specifying the cellular phenotype have a great deal to do with physical state at which the latter process takes place. It is because of this, for instance, that the deterministic assumptions of the genetic program model of development are completely unrealistic. It is just not possible, physically speaking, to compute the embryo from a complete description of a fertilized cell's DNA sequence and the location of all of its proteins.
Hang on a second. I just want to highlight that. Okay. Very important. Okay.
One reason for this is very simple. Gene expression is first and foremost a molecular process, and like all molecular processes, it is subject to the dampening stochastic effects of Brownian motion. Let me elaborate this point a little.
Okay. So the idea of a blueprint or a genetic program. Okay, I think when I got into molecular biology a while ago, prior to that, I had this idea that the gene was somehow a blueprint for how to build a hand. And then when I started learning a little bit about it, I started to wonder how in the hell can this nucleotide sequence build a hand? And it isn't until you get into embryology that you see that isn't what happens at all. It's nothing like a blueprint at all. It's almost impossible to find a really good analogy for what happens. I can't think of, the only thing I can think of is a very, very small little programs that tend to build, bigger things because of the repetitive nature, but it's very difficult to envision how this thing really happens. And I think he's pointing out that The other problem is, the idea of a computer. You have code, and you have something. You have a processor that reads the code byte at a time and goes through this stepwise motion, right? And computes some in an accumulator. It computes sums, and that's pretty much what happens. And it's very difficult to see how that could happen in molecules. It doesn't. So not exactly how it happens. So anyway, Scott, you want to take over? Or?
I don't mind doing another one, but it's up to you.
Go ahead. Go ahead.
Gene expression. Yeah. Gene expression is an extremely intricate process. Consider how it gets started. An inducer, which can be an intracellular or extracellular signal, triggers a chain of biochemical reactions that causes proteins, called activators, to bind to specific sites in DNA known as enhancers. Upon binding, the activators interact with other proteins that recruit RNA polymerase and its associated transcription factors to the promoter region of the target gene, where it then begins to process the process of transcription. Numerous additional steps need to be strictly followed after transcription, including RNA processing and export, translation and protein folding, and sorting. The point is that for even a single protein to be successfully expressed in the cell, a huge number of molecules need to interact with one another in exactly the right way and at the right time, and in exactly the right order. It should not be surprising that the likelihood that all of this happens in a perfectly efficient and precisely timed fashion, as one would expect, happens as one would expect of the programmatic execution of an algorithmic sequence of coded instructions, is virtually zero. We take into account the random and ferocious buffeting that all molecules are subject to inside the cell by virtue of their size. The impact of stochasticity on gene expression is exacerbated even further by the fact that a cell, unlike a test tube, contains very low copy numbers of the relevant molecules. There are only 1 or 2 copies of a given gene in any cell, just a few copies of each mRNA molecule, and a few dozen copies of the required polymerases and transcription factors. Consequently, it is not possible to appeal to the law of large numbers to make accurate predictions about the process. Of course, it is still possible to make predictions when gene expression is measured across a population of cells, as the individual differences between cells are averaged out, but this becomes impossible when measuring the gene expression of the expression of a gene in a given cell. The recent introduction of methods capable of tracking individual molecular reactions on a cell-by-cell basis has confirmed that even genetically identical cells, subject to the same external conditions, exhibit substantial variability in their gene expression in their gene profiles due to the inherent stochasticity of the process. This finding makes perfect sense given at the scale which gene expression occurs, but it is difficult to reconcile with the genetic program model, as 2 identical computers running the same software are expected to execute it in exactly the same way.
Now, another thing that we might mention here is the ENCODE project found that, there's transcription like at about 80 or 88% of the of DNA across a number of cells. Of course, they went across 200 cells, right? Or 200 tissue types. But there is a whole lot of spurious transcription and probably spurious translation into proteins. So there's a mess of things that would differ in every cell, and the whole thing adds up to a sort of an averaging process on this stochasticity, and the cell either stays alive or it doesn't. And of course, if it doesn't, it's not an issue. It goes away, gets reproduced. But there's a whole lot of things going on that don't lead mechanistically to the result that the cell perhaps needs, or that we might think the cell needs. So does that make sense?
Yeah, it does.
Yeah. And that's also the place where every now and then those accidents can add up to a pathway that actually works and does something. So, and that's one of the things that I become increasingly interested in, is that possibility of new pathways. So anyway.
Yep.
Scott.
Frustratingly.
You keep going. As long as you want.
Frustratingly, instead of questioning the theoretical adequacy of the genetic program or the assumptions that underlie it, molecular biologists initially reacted to the discovery of the stochastic character of gene expression by borrowing an additional idea from the realm of engineering to make sense of it, namely the concept of noise. In engineering, noise refers to an undesirable random disturbance that garbles the transmission of a message. Noise is therefore a nuisance that engineers strive to overcome by designing machines that filter out its detrimental effects. The rationale for appropriating this term seems to have been that stochasticity thwarts the capacity of molecular biologists to perfectly predict cellular behavior in the same way that noise thwarts the capacity of engineers to design and manufacture totally predictable machines. In any event, the analogy does not hold because cells, unlike machines, actually benefit from the noisiness of gene expression. Far from being disruptive or detrimental, recent research has shown that gene expression plays many crucial biological functions. In microbial cells, it is a key generator of phenotypic diversity within populations, and therefore serves to increase their adaptability to new environmental conditions. And in eukaryotic cells, among other things, it helps to determine cell fate decisions, thereby shaping the way in which cells differentiate during development.
Nice. Okay.
Overall,
yeah, that's a good summary there. Noise is nice.
Yeah, noise is nice. Yeah. Well,
I'll just read this last one.
Noise is evolution.
Noisy evolution. Got it.
Yep.
Overall, the genetic program can be understood as a rather crude approximation of what happens during gene expression. Although the metaphor does compellingly capture the order, reliability, and robustness of this process, it does so at the expense of abstracting away the messy molecular details that enable it to take place. Upon close inspection, the analogy with how a computer executes a program breaks down. Luneton, as ever, puts it best when he declares that any computer that did as poor of a job of computation that an organism does from its genetic program would be immediately thrown into the trash, and its manufacturer would be sued by the purchaser. It is worth pointing out as well that the genetic program metaphor misrepresents not just the phenomenon it seeks to explain, but also the way in which scientists seek to investigate it. Molecular biologists are not simply in the business of deducing computable functions, either mathematically or algorithmic, from their empirical studies.
Okay. So we're coming up on 50 minutes, which is a good chunk for a paper. And
yeah.
Do you want
circuitry.
Do you want me to lightning round metaphor 2?
I think cellular circuitry. I think we want to spend a hell of a lot more time on this one because we get into like the diagrams and a bunch of other stuff. I would like to spend more time on it and do a little prep for it and get some highlights in advance. And take a look at cell circuits for one would be nice. I don't know.
Okay.
Have you ever found a really good description of how they write these things?
Nope.
I found a program that actually writes them. And in that program, I have the documentation for it. And I'm kind of hoping, for one thing, if you have a little flat bar like this black thing up here, and if you can see my mouse, you can't see my mouse on this damn thing. Like where it goes down and there's a flat bar instead of an arrow, that means it's an inhibitor. And if it's an arrow, then it's, an expressor. But I am not entirely sure what those little triangles on the bottom are. The little white triangles. And there's a few other things like what is a different, a dashed line, I guess, would be another pathway or a lesser pathway. But if you look at these little circuits that we come up with in biochemistry, you think you would have covered that somewhere. I'll see if I can find the site. There's a site where you can get a program, download for free, where you can actually create these diagrams. But it's really kind of a little devil to use. They do have a tutorial, but anyway, they're kind of cool. These are like, and oftentimes these are pathways, multiple cells overlapped one upon another. We're in one tissue type. And I think CRISPR pointed that out to me at one point. One tissue type, it will be active, and another tissue type, it wouldn't be. So, but these are pretty important.
Isn't Nicholson's thesis, though, here that such diagrams actually restrict the amount of useful information you can get from them because it assumes basically it's blocking out noise. In other words, it's only showing one pathway or whatever that can be followed rather than what the other noisy elements accomplish.
Right, they're deceptive, and that's why biochemistry often leads you to believe that a cell is more like a machine because it's filled with these pathways. But they're also informative because they're going to tell you what mechanisms that they've already figured out and delineated. So in order to learn one of these pathways, you have to figure all that stuff out in order to get an overall idea of what's going on. But then if you take your if you're pointing at the moon with your finger and you mistake the finger for the moon, that would be taking this seriously as a little circuit diagram. Because if you put together a circuit like this, if you could somehow electronically make a cell, the cell wouldn't work. For one thing, there's a lot of shit that's missing. There's a lot of noise that's missing. And there's a lot of other elements that go into, how these things work. So if you built a machine that worked real cleanly according to this diagram, I think it'd probably fail all over the place. It wouldn't produce the right amount of stuff. It just wouldn't work. So we don't want to take our diagrams too seriously, but the diagrams are important. And, if we can teach people how to read them, that would be cool too. So do you think?
Well, it just depends on your didactic goal or whatever. What are you trying to teach, and how far does this diagram, the circuit, go in teaching that particular concept? And I guess there's a cost-benefit ratio too. Of are you thus creating so many misguided impressions that you're actually doing more harm than good educationally?
Yeah, showing something like this to a person without talking about any of the other stuff, that would definitely be not informative. But in fact, if you wanted to understand what's going on in this diagram, the first thing I would do is get rid of this diagram and get a simpler one.
Mm-hmm.
Start out what happens with Fox A here and Gata E and stuff like that, and Hox 11, and not look at the whole goddamn thing. This looks like a developmental diagram. It's got Notch and it's got Hox, and what else does it have?
Yeah, early development of a sea urchin embryo.
Yeah, like the Wnt8 pathway, that particular pathway up there on top, that one is used in so many different things. It isn't just used developmentally, but it comes into play in cell death and cell division and a whole bunch of other things. It has a number of different functions. That's the other thing, that each of these little circuits behave differently in different conditions and different pathways. So, but a lot of it is, pretty messy and stochastic, and that's why we keep finding, like, the creationists famously, say, "Oh, they discovered this, they discovered that, they discovered this. It's so much more complex, so much more complex." Well, the complexity is never going to end, because by the time we figure out what is happening in our cells today, our cells will be doing something different in 50 years. So they'll find new things, or they'll find new things that are happening in me that aren't happening in you. Hence, I can get away with eating bacon where it might kill you, that sort of thing. And there's
what a way to go.
So, I mean, even if we figure out what's happening in one human being, we wouldn't necessarily be able to cure cancer in the next one. And that is the problem with curing cancer. And it took me a long time to forgive science for not having cured cancer yet, because the goddamn thing just has so many different ways to happen.
Yeah.
That even if you found them all, a new one would pop up tomorrow, Yeah,
because cancer is not like bubonic plague. There's not one thing behind it,
Right.
Yep. It's cells going wrong in as many ways as there are cells.
Yeah, and if you were to come up with some sort of a drug that cured cancer, it would also cure life, because a lot of those mechanisms you rely on to sustain your tissue types and your skin and your organisms. It's just that they tend to stochastically run away on us every now and then. What would a machine example be? Suppose if you had a a Ford factory producing the 2020 Ford whatever, and it all of a sudden started going nuts and producing all fenders, like millions of fenders, until the factory burst open. That's
wow.
Yeah,
and
that would be yeah, that would be a cancer analogy. So
that's right.
Anyway, so I think that covers it for today. I think that would be a good one. I'm going to have to rename this as part one. And hopefully next time we can go through, if not all the paper, how much we got left? We can go through at least another third of the paper. We'll try to break this one up in 3 parts.
Yeah, and I'll try to provide more of an overview kind of outlook as well, rather than having to read exactly every word.
As long as it's every now and then my PDF reader saves my highlights and sometimes it doesn't. I never quite figure out the difference.
Yeah, so that's annoying. But
I think if you move them to another folder, it loses the highlights. I'm not sure. I don't even know how they store highlights. They store it in metadata for the file on the Mac, I think. Like they have tags and things like that. So I'm not entirely sure how they do that. Should look into that. Anyway. Okay, boys and girls. What do you think?
I think this is a good paper. It's a good chapter. It's enjoyable to read. The only thing is towards the end when he starts taking issue with Schrodinger, or what scientists have done in response to Schrodinger, I don't think he really makes a case. I think it's highly speculative, and I really wish he had provided some documentation of that effect on the scientific community. It's a good, like I said, it's a good speculation, but I'm just not satisfied that he has put his finger on a real cause or a real cultural shift or whatever.
Yeah, again, I was really amazed when I read in that book this afternoon on entropy in life, that how he came down on Schrodinger for creating a nightmare, basically, with entropy. But he came down on a whole lot of other physicists too that are basically, as he would put it, if he were honest, talking out of their asses. So it's kind of cool. Anyway, okay, boys and girls. We are going to end the broadcast. Anybody have anything final to say? Nope.
Wash those hands.
Goodbye, cruel world. Long live Frank. Frank is dead.